I've been working with SIG for about 11 years now, and started out in computer engineering, worked at John Deere briefly, and then discovered seasonal wildland firefighting during college, and haven't really looked back from that. Got into fire ecology from there. Worked for the Forest Service and the Nature Conservancy at UC Davis for several years, and then eventually moved back to Iowa, where I'm from, and then started working with SIG. So that's how I came into this job, and it's been a lot of fun, and I've learned a lot and really enjoyed the opportunity to work with all of you guys. Okay, and Megan's running this, so I'm going to have her run the slide. So FCAT stands for the Forest Carbon Analysis Tool. This is a working name that my wife came up with about a year ago, and it's kind of stuck with us for a while. So unless somebody's got a better suggestion, that's gonna continue to be the name that we use. Initially, FCAT was intended solely to be used as a tool for automating the modeling processes that go into REM. REM is a carbon accounting framework it stands for Reduced Emissions from Megafires. And this is really Thomas Buchholz's project. He's been working on it for many years. And it's a forecasting methodology that is used to help provide funding to implement fuel treatments in forested areas to reduce the risk of severe wildfires. So these fuel treatments can be things like prescribed fire, mastication, where you shred shrubs and things into small chips, or thinning small trees, anything that you can do to reduce fire behavior potential. The key thing here that differentiates it from typical carbon offset projects is that these are intended to provide funding today for what are expected in the future in terms of reductions in greenhouse gas emissions. So to quantify our expectations of those reductions, we do a whole series of modeling steps that are described in this protocol. And that's where FCAT came in, was to automate and really streamline this process of quantifying the components of this REM protocol. It's expanded beyond that. REM is still its main focus, but there are many other applications for what it can do. What I won't cover in this talk is the details of the protocol. That's probably worth a talk on its own by Thomas. I also won't talk about how to run FCAT as a tool or the specifics of how it works. My goal here is just to kind of provide a demonstration of what it can do and give all of you some ideas of applications and just a demonstration of some typical outputs. Okay, next slide. So this slide shows an example of some of the components of the REM protocol. I won't go into the details here, but this shows how the REM protocol tracks carbon in different pools and produced by different sources over time, over a 40-year project span. And the idea is to be able to quantify overall, over all these different pools, what is the benefit in terms of reduced greenhouse gas emissions over time, over this full 40-year period. So that's about all I'm going to say about the REM protocol itself. But that kind of gives you a sense of what we're trying to do with this, is track all these different pools and how they're affected by these fuel treatments. All right. So what is FCAT actually? Officially, it's a command line tool that automates this process, as I described. The modeling is what enables project applicants to apply for funding, and they have to quantify all of these different components of greenhouse gas emissions. Along the way, it uses a lot of GIS processing. It uses the forest vegetation simulator, which I'll describe next. And it does a lot of Monte Carlo grid fire simulations to look at burn probability and different aspects of fire behavior. It uses a Forest Service smoke emissions tool called FOFEM, First Order Fire Effects Model, to look specifically at smoke emissions. So that's what FCAT was originally designed to do. It can do more than that, but really effectively what it is a tool to run spatial simulations of forest growth and yield. That's kind of the heart of what it does. I presented a talk on this last year, about a year ago, at the FES Users Conference, and I've worked closely with one of the FES developers as I got going on this to explore ideas for how to run FES spatially. And according to what he said, there really aren't too many other companies in the country that can do exactly this. So that's what makes it unique, I think, for SIG, is that we have the opportunity to do things with FES that are pretty cutting edge. FES has been around forever, going back to 1973. The Forest Service developed it and still maintains it, and it's evolved substantially since then. But at its heart, it is a collection of tools implemented as software models to look at forest growth and yields via simulations. It tracks individual trees, but it does this within stands. Where they are in the stands is not tracked. What it requires as far as inputs is tree inventory data. So some description of what species, what size these trees are, whether they're live or dead. Often this comes from field data that's collected from plots across certain project area. And then what FES can provide from that data is a description of stand level forest conditions described in typical forestry metrics. And then more recently, it's been expanded to look at things like carbon stocks and various fire behavior metrics, effects of wildfire on trees. Also, you can simulate the effects of timber harvest or field treatments, and you can do all this over time. So you can project these effects and these changes through time into the future. Okay, so typically FES, or typically users would run FES via its web interface. And this provides a handy way to run plot level data and produce some nice little visualizations. We don't usually do anything with these visualizations, but it's kind of a nice way to look at some of the outputs. And really, its primary outputs are tabular. It all comes out in a database. So a lot of what FCAT focuses on is taking that spatial or that non-spatial database and converting it into a spatial representation. Next slide. And what FCAT is not, it is not complete. We're still in what the software team is calling pre-alpha, so we're not even into beta yet. It works, but we're still working out some details and just making it easier to use and finishing up some details. It is also not able to handle non-forest vegetation. It is entirely focused on trees. So it does do some very basic things with grass cover, herbaceous cover, and shrub cover, but at its core, it is entirely focused on tree and forested landscapes. It is also not yet an easy-to-use graphical user interface. It is a command line tool. It's getting easier to use, but I know eventually the goal is to make this into a GUI-based tool that anybody can use more easily. That's still in progress. All right, so here's a brief overview of the history of FCAT and how it came about. This really started with Thomas and I working on REM projects. REM didn't exist. REM as a protocol wasn't approved until March of last year. So we call these REM-like projects because they basically follow the same protocol as that protocol was evolving, but they weren't really being designed to be funded through this market mechanism. We did that for several years. It was a very manual process. It required a lot of work on Windows, Microsoft Access, FES on Windows, which always crashed. And it was a kind of a painful process. And it took a long time. It was difficult to replicate. If there was a small change that needed to be made, essentially the whole process had to be started from scratch. And it might take months of pretty manual work to get through a project. Around 2018, the Forest Service released Tree Map, which is a CONUS-wide raster, essentially, of FIA, forest inventory and analysis data that is imputed across the entire country. And It's a spatial representation of tree inventory data from these FIA plots. So we now have a spatial input data set, which was what limited us until 2018 or so. And then around that same time, the Forest Service released a Linux-based version of FES, which really allowed us to begin scripting a lot of these tools and making the process much more streamlined. At that time, I started to script the process in these different languages to make it more replicable. The idea was, at this point, it was still just me running it on my local machine, but it was becoming easier and easier because we had a set of tools that would do the same thing every time with different inputs, and it was much less dependent on manually run GIS processing or manually run simulation efforts. And then around 2022, JPWAC started working with the software team to extend this from just something that I used to something that anybody in SIG could use and make it much more formal and well documented, and just trying to expand its use, essentially. So this was my poor attempt to document what I initially did, and for a long time, this was all there was really of FCAT documentation. It was literally 3 sheets of paper that I taped together with a hand-drawn sketch and a schematic that outlined the basic modeling process. And it was a mess. It was a disaster. No one could read this. I couldn't read it. After that, Jordan Combs took over from JP, and he produced a very nice schematic to replace this on the next slide. And that shows the whole process in a much more understandable way, and it cleaned it up, and it made it so anybody could look at this and really begin to understand how all these different models integrated, and we could begin to think about how to shift all this compute processing onto virtual machines and make it so that others could use it easily. So that was a huge step forward to implementing most of these scripts in org files, which was a huge improvement and made it possible to execute different blocks of code from an organized system that lived on a virtual machine, and took those 20 scripts and made them, or roughly 20 scripts, and made them much more well documented. The documentation was integrated right into the code, and made it easy to execute those. In that fall, I began working closely with Alice, and we took those scripts, primarily Alice, and improved them, and made it possible to run these in a microserver environment. And I'll get into the details of that in a second, but the idea was that anybody could call these scripts without knowing anything about the scripts themselves in a framework that would let them do this remotely from their local machine. Also that fall, the name changed from avoided wildfire emissions to reduced emissions from megafires. The idea was we didn't want to make people think that we were trying to eliminate all wildfires or all fires, because in some cases fire is quite beneficial. So the name changed to what it is today, REM, for the protocol itself, not for the tool. And almost exactly a year ago, FCAT became fully functional as a tool, as a microservice collection of tools that anybody could run. So today, that's where we're at. Anybody can use FCAT remotely from their local machine if they're on the VPN. Kayla Johnston coordinates training and the use. There's several people, a growing number, that can use FCAT, and it's still not as easy as it will be, hopefully. We're still going through some growing pains, but it's definitely improving and getting easier to use. This is a topic for Gary, and I'm sure he'll get into this more with his lunch and learn presentation, but I just wanted to explain briefly what microservices are. They're essentially servers running on remote virtual machines that do nothing but wait for job requests. So as soon as a user submits a job request, that microservice takes the user's inputs that are project specific and then sends those to the scripts that are written and runs those for a particular project. FCAT is not the only microserver type software that's available now within SIG. There are several others that the software team has developed, Cameo and an online version of FES that's been working for quite a few years now, as well as a lot of the Pyrocast tools are based on a microserver architecture. So the main goal is that anybody can run these. They don't have to rely on local hardware. And this is done via simple commands that are executed by any user, and then they specify the project level parameters that they need for that particular application. Okay, so for the next few slides, I wanted to provide a demonstration of what FCAT does and maybe kind of prime the pump a little bit to get people thinking about how they could use it if they're interested in applying it for their particular region or use case. I focused here in just a quick demonstration based around the Lake Tahoe Basin Management Unit. That's a Forest Service designation for the watershed around Lake Tahoe. Lake Tahoe is an alpine lake straddling the California-Nevada border. And it's high profile. There's a lot of SIG work that's happened there. And I just picked that as an example landscape that a lot of people should be familiar with, I think. There's the size. It's about 130,000 acres of forested lands. What would have been essentially impossible to do with with FES Online, which is the web-based version of FES. There's no way you could have done a spatial FES simulation of every 30-meter pixel across an entire landscape like this. But with the spatial version of FES, we can do that now in about 5 minutes for a particular simulation. So the compute time is manageable, and we can do some pretty large landscapes at high resolution, which is where the advantages of FCAT really shine, I think. So this shows the first step of what FCAT does, and it's basically updating the 2016 conditions represented by the tree map raster data set from the Forest Service, and that brings it up to the current year or whatever year you want to start from. And it does that by applying disturbances that have occurred after 2016 and before your start date. So we've got data from Fire Factor and a number of other SIG products that provide spatial descriptions of these disturbances. So the left panel shows what canopy cover looked like across the whole basin, which is inside that black perimeter around the lake. The darker the green, the higher the canopy cover. That was conditions as of 2016. The middle panel shows a few polygons in the northwest corner, as well as the footprint of the 2022 Caldor fire that burned south of South Lake Tahoe. And the colors there represent different fire severities. So that's satellite data that has been compiled by SIG people. And the red shows a particular location where the fire severity was high. So the next rightmost panel shows what canopy cover looks like today, as far as the best we can produce, at least with tree map data and FES. So in general, you can see the green is a little bit darker as canopy cover has increased over time, except within the footprint of that fire south of South Lake Tahoe. And you can see the effect of the fire on the canopy cover in that region. So this process is automated by FCAT and essentially brings it up to today's conditions. Eventually, tree map will be released on a more frequent basis, but right now all we've got is the 2016 data. Next slide. This shows the same three data sets, except zoomed in on the footprint of this Caldor fire, and you can see how the effects of the fire severity on canopy cover. So it definitely works as it's supposed to, and it reduces wherever the fire severity was high. You've essentially lost all the canopy cover. All the trees were killed. Incidentally, this is maybe a mile or so, a couple miles from Shane's house, which I think is pretty close to the arrow. So we got a little closer comfort with Caldor fire.
I can also note the canopy cover is not represented in the urban boundaries very well. And I think you were going to make that point, Dave, but I just want to make sure you remember that.
I was going to, and I forgot. Yeah, thank you. So can you go back one slide, Megan, just for a second? That's a great point. If you look at either the left panel or the right panel, you'll see that there's a lot of blank areas shown around the shore of the lake where there's obviously trees in the satellite data. This is because tree map is partly dependent on land fire data. Land fire masks out all urban areas. So as a result, we don't have tree map data in whatever areas land fire classifies as urban or any kind of developed landscape. So even though there are obviously trees there, we just don't have data to simulate areas like South Lake Tahoe or some of the bigger cities on the North Shore. So yeah, thanks. That's a good point. All right, okay, next slide. Great. So FES produces a huge range of outputs. I just picked these 5 as representative of some of the different kind of categories of FES outputs. The first I chose was canopy cover. You just looked at those. That's a typical forestry stand metric. It's important for a lot of reasons. And that's one that's easy to look at because it is obviously affected by a lot of different changes by management or by disturbances. Stand density index is an example of a more ecological metric, and it's useful to get an indication of where stands are so dense that they've lost resilience. They're basically so dense that they're competing with each other and at risk of increased mortality due to drought or other factors like insects or disease. Total stand carbon, obviously that's an important one for carbon accounting. FES will track carbon in a lot of different pools, and then it summarizes those as total stand carbon. So we'll see some maps of that. The last 2, probability of torching and potential smoke production, are examples of some of its fire behavior outputs. These are purely stand level. There's no component of fire spread simulated by FES. So this is just what happens if a particular stand or point on the landscape were to burn. What would happen, or what kind of fire behavior would you expect to see from that, and things like smoke. So we'll jump into that next. Here's stand density index. The blues are the lowest SDI values, and then you get up into the more yellow and orange and red, it's higher. So if you wanted to make this a little more relevant, you could compare this as a ratio of the maximum stand density index. And there's some great resources that show how the risk or how the resilience of those forest stands change as they become more dense. So that's a really useful metric for a lot of reasons. The next one shows total stand carbon, and this is in tons per acre. So if you were interested in knowing where is carbon in forested landscapes at Lake Tahoe Basin concentrated, this would be a good map to start with. So the darker the green, the more total stand carbon in that location. And I wanted to point out too, these happen to be 2024 that I picked to show. You can project this into the future and show how you'd expect total stand carbon or any of these metrics to change over time as a projected expectation. The next one shows the probability of torching as a percent. So 0% is blue. There's a few spots like within the high severity area of the Caldor fire. You've essentially lost the potential for that area to torch. Torching means a fire has transitioned from the ground up into the tree canopy and it's burning individual trees. So a large portion of the forested Lake Tahoe Basin area is at risk of, pretty high risk of torching. The next one shows potential smoke emission. This is what would happen. It's basically the conditional expectation of what you'd see if that particular location burned given certain weather conditions. And another useful thing to look at, if you wanted to make sure that you were focusing on areas in which to apply field treatments, to reduce smoke production during wildfires. This would be a useful map to help you prioritize areas, which is what Planscape does. So this is kind of being built into Planscape too. So similar approach to what Planscape does there. This shows a summary of some of the data for those particular metrics that comes out of the FES database. And you can see over time, if you start into the rows are different years, row 2016 up to 2024, you can see canopy cover changes a few percentage points over the years, and then total stand carbon increases as you'd expect. It's just because these trees are getting bigger and denser, forests are denser. Stand density index, you can see changes and increases over time as well. Probability of torching, that's a function of how dense these trees are and how high the canopy base height is. Increases, not dramatically. Same with smoke production. And if you're curious about the total amount of something in the landscape, you can also summarize the FES data and say, in a given year, there's roughly 10 million tons of carbon in the forested lands. And then also you could estimate how many 1,000 tons of smoke production you'd see if the whole thing burned. Next slide. So there are some unnecessary but kind of interesting statistics that you can get out of FES and the tree map data as well. And these are just a few that I picked out that are kind of fun. There's a total tree count for all the trees mapped by tree map in the basin. And it's something like 43 million trees. And roughly 5% of those are dead as of 2016. FES will simulate trees dying, so that number will change over time. And then if you're curious about the distribution of tree species in a certain location, like the basin, you can summarize it by different species and see that, for instance, lodgepole is roughly 30% of the trees. The firs are the next largest component. Makes sense. Tree map is not necessarily known for its accuracy in mapping tree species because it's imputing plots from all over the West. Some of the species can be pulled in from other states or other regions. Generally, they're pretty close, but every now and then there will be some species mapped that really don't make sense. That's Jarrett next to a gigantic Jeffrey pine, somewhere in South Lake Tahoe area. Next slide. So if you're curious, you can even do some tree hunting here. You can find the biggest tree as of 2016 in the basin, and it was a 135-inch giant sequoia. Highly unlikely that it's actually a giant sequoia. It's probably more likely to be a sugar pine or Jeffrey pine. And you can even find where those are. So if somebody wanted to go out there and find those trees, there's the coordinates. And interestingly enough, those trees were mapped as dead in the tree map data. And that's within the footprint of the Angora fire. So I did some field work there a long time ago, right after the fire. 100% certain that it's not a giant sequoia, but there are definitely some big trees out there that could be found. Most likely not giant sequoia. This shows some other data that you can get out of FCAT, and it's kind of cool. You can see the percentage of your total area by forest type and by year. So if you're curious how forest types change over time, they're pretty static. FES assigns these forest types according to the distribution of species within the stand. As trees die and are recruited in stands, that distribution and makeup of tree species changes, so that the distribution of these forest types does change, but pretty static. And you can see that California mixed conifer followed by white fir are typically, over time, the dominant forest types in this region. And the next one shows similar data by total stand carbon. So here you can see that California mixed conifer holds the majority of the total stand carbon in the Lake Tahoe Basin, followed by white fir and red fir. And these do change over time. So every year that level of total stand carbon increases. What's interesting too is if you look at the average total stand carbon, meaning the density of carbon, so tons per acre, It's actually red fir in the table in the overlaid on the plot there. Red fir is actually the densest, the most carbon dense of all of these forest types. The only reason that California mixed conifer is higher is because it's got so much more land area than the red and white fir. But yeah, if you're curious about different forest types to prioritize for protection or management, you could see that kind of data with what comes out of FES and FCAT. Okay, so what was shown so far is interesting, but kind of cool. What's next, I think, is even more interesting. You can actually project into the future, and you can look at different effects of management. So it's more of a what if scenario. You can game out different scenarios and start to think about what are the effects of management or different disturbances, and let FES produce these, model these changes as a function of these different factors. So for this particular case, I just picked 3 locations somewhat randomly across the basin. These and I looked for areas that were high in stand density index, with the idea that if they were high, they would benefit from being thinned, both from an ecological resilience perspective and also from fire reduction perspective. So this is a pretty simple prescription, but I let FES thin trees within a certain diameter range, 3 to 16 inches, down to a certain level of stand density index, and then simulated a prescribed fire after that to reduce the surface fuels on the ground. So this is where you can see some effects in a hypothetical way. So there's the 3 spots I picked, 2 on the west shore and 1 very far south, where the stand density index is fairly high. Next slide. And you can see on the left what the probability of torching looked like before treatments, and then what it looks like after these treatments. And in this case, the treatment was very effective. Those blues mean essentially no chance, like a few percentage points probability of torching. So very effective. You could try different treatments and see how that affects your expectations. The clip from a database query on top shows within these 3 treated areas, which are about 8,000 acres, how does the canopy cover change? It's gone down slightly. How does the average total stand carbon change? Dropped about 20 tons per acre of carbon. So that's your cost of doing these treatments if you want to think of carbon accounting. You very successfully reduced STI down to almost 200, which was your target, and very effective at reducing probability of torching and smoke production. And here's the same data shown with spatial data for the smoke production. So pretty effective at reducing that within the footprint of your treatments. All right, so a couple last slides here. These are some of the uses of FCAT that we've done within SIG so far. REM obviously is the focus, and we've done lots of feasibility projects, cut the runtime down to a day or 2 for those. And hopefully soon we'll be doing some real projects that will go to market. Landscape, we'll use FCAT to quantify direct and indirect effects of fuel treatments. It's part of the million acre strategy. It's being used right now for the wildfire crisis strategy to look at the effects of fuel treatments that were actually implemented across 21 different landscapes in the West. One cool thing you can do is you can look at what would have happened in a real wildfire if a planned treatment had actually been implemented. So we know the effects of a wildfire because it burned, and we can measure those effects. What we can't do easily is look at what would have happened if some kind of fuel treatment had been implemented that was either litigated or unfunded and never actually implemented. So this is a way to quantify those effects. A couple other projects, CBREC, Carbon Team is using it to do some feasibility analysis. It's useful for NEPA for looking at the effects of different alternatives for different management. Next slide. And in the future, we're working with Jeff and the software team to improve the architecture with the use of Kubernetes to make the compute power available to FCAT more scalable and ramp up on demand as people use it more. We're hoping to automate some other uses beyond REM to make it easier to do those kinds of analyses. Hoping to improve the use of FES. It's got some shortcomings like tree regeneration and fuel models that we'd like to improve, and a couple other goals that are listed there. But I think I better wrap it up in case there's any questions.
Okay, well, thank you so much, David, for presenting. We've still got a couple minutes for questions, and it looks like Thomas has a question.
Yeah. Hey, Dave. Nice presentation. So in that treatment that you inputted into the scripts, it was thinning and a prescribed burn. Are you able to segregate out from the effects of those two, or do you have to do two separate runs?
That's a great question. Yeah, if you wanted to look at something that was tied specifically to the prescribed fire, like smoke emissions from that prescribed fire, you can quantify that without having to run them separately. But as far as changes in, say, canopy cover or stand density index, you'd have to separate those into two different runs to fully disintegrate those effects.
Okay. Right. Thanks.
Yeah.
Jason.
I'm here. Hey, Dave. Thanks for everything you guys are doing on this. I think at some point, is there going to be a way, or maybe we have it, just to generate standard prescriptions, like, for salvage, reforestation? They're all, like, you've worked with these projects we do, they're almost all the same. They're just different national forests, different fire severity. It's a little different. So.
Yeah, for sure. So every time we run a different fuel treatment in FES through FCAT, we save the description of that particular prescription. So we're building up quite this library. I think there's a couple hundred different prescriptions that are saved now that we can reuse easily and not have to start from scratch. So we can either modify one that exists or just use one that's already built. But as we go through time, we'll have a nice library of those pre-built.
Cool. If maybe offline you could share just the input, because I could probably populate a few for you on this upcoming.
Yeah, that'd be great.
Chris, you had a question?
Yeah, on the hi, Chris Scow. I work with Jason and Shane and whatnot. When you went over the thinning and prescribed fire on that stand south of the lake and mentioned the carbon cost of doing the thinning and prescribed fire, the obvious interesting question would be to weigh that against not treating it, not thinning, not doing the prescribed fire, and seeing what's lost in a crown fire, taking out the whole stand as it is. So I mean, that seems like a pretty simple way to show the carbon benefits of losing a little bit of carbon versus losing all of it. So
Exactly.
I'm sure you've thought of that. Sorry.
Well, that's actually, yeah, I didn't go into the details of the REM protocol, but that's exactly what that protocol does. And it simulates wildfires, high severity wildfires at every 5-year time step across that 40-year simulation period. So you basically have a quantification of what would be the effects in terms of carbon and smoke emissions and delayed reforestation and some other things of a high severity fire at that point in time. So you're not biasing your estimates based on only when your fuel treatment is effective, but you're also looking at the case where you're 20 years or 30 years past your fuel treatment and it's become less effective. So you're kind of weighting the effectiveness of your fuel treatment over time and running all those hypothetical scenarios and then summarizing the results to quantify hopefully a reduction overall in emissions.
And then can you, sorry, you made me think of something else. After all fires, they are required to do a field treatment effectiveness study on, I think it's 10% or something like that of the field treatments are impacted by the fire. It'd be interesting to compare what you just described to some of the literature in field treatment effectiveness done post mega fire, because especially in Region 5 in California, there's been a lot of people get their masters in fire ecology by doing post-fire field treatment effectiveness. I know on the rim we had a bevy of people doing that, and I'm sure on the other fires. Anyway, thanks for the presentation. It was awesome.
Yeah, for sure. Yeah, thanks for listening. And yeah, it'd be great to calibrate or validate the results with real world data like that. That'd be an interesting project.
Go ahead, Thomas.
Hey, Dave, what's the plan for extending it beyond the US?
We're limited by FES. FES does extend into Canada. It's just parts of Canada, and I don't know how well parameterized it is versus the Western US, where it's been, and actually most of the US, where it's been used for decades and really calibrated against field data. Other than that, we're also limited by tree map or some kind of spatial tree inventory data. So if that would exist for another location and we had a good model, it wouldn't have to be FES necessarily. Then we could do something like this. But right now, I'm just not aware of any other alternative models and data sources.
Okay, thanks.